Fantastic. Thank you very much indeed. Hi, everyone. Thank you very much for coming to see me. The token slide, I'm Will, online pretty much anywhere I'm stealthploit. I co-founded a cybersecurity company, UK-based one, in 2018 called In.security. I'm a pen tester by trade and a trainer, and before 2014, which is when I defected to the dark side of hacking, I was a digital forensic investigator. I've been really, really lucky and humbled to have trained and or spoken at a number of places. And as of today, SecT speaking, thank you very much. We've been training here, which is fantastic. But it's been a great crowd so far, so thank you for having me. I also managed to socially engineer my way into a DEF CON invitation this year to help run Password Village. I'm modeling the Password Village t-shirt just to prove that I was in fact there. But let's jump straight in. As you will have guessed from the title of today's talk, this is going to be about password cracking. I'm not going to be covering any basics. How do you crack a password? We're going to be looking at more creative, more fun, more unorthodox things. A few of which are labeled here. Including a particularly nice attack, which has been around for a while, but slightly lesser known, coming up towards the end about using hashes to crack hashes instead of word lists. So hopefully we will have some fun. But we are going to jump straight in the deep end, with some Midway incrementing masks. So this can be a bit of a tricky one, because when you're running mask attacks or brute force attacks in hashcat, you can increment where you start and finish your mask. However, it's very hard to get fixed character position or fixed character set placement. So for example, if you know that your password you're trying to crack starts with, in this case, an upper alpha character, and you know it ends with a special character, but you don't know how many characters are in the middle, that can be a bit tricky to implement. One possible solution, and there are probably more ways as well, is to do what's shown here. So what we can do is we can take either our fixed character, or in this case, an upper alpha character set, and actually use that as a dictionary. In this case, the dictionary is called upper.txt. So whether it's upper or whether it's decimals, in the screenshot, I appreciate they differ here. We can take our fixed character set, we can apply that, and then what we can do is we can actually pipeline hashcat. So a lot of people don't realize that you can feed multiple things into hashcat. It's not a static application you need to run as is. So in this example, we're taking a fixed character set to start with, incrementing our masks. As we can see here, we've got the question mark else for lower alpha, but the dash I means increment. But instead of cracking a hash, we're going to put that to standard out and then pipe that into hashcat, using a rule for our special character at the end. So this is quite a nice way of getting around that. You do need to be aware, though, that there is a limit to how many lowercase alpha letters you can have in this instance, because you will quickly run into an integer overflow if you try and attack too many. Let's have a look at Expander and Princeprocessor. So Expander is a tool that's been around in hashcat utils for a very long time, and it's absolutely fantastic. We can see some examples of this on the right. On the bottom here, what this does is this takes a word list, splits, mutates, and reconstructs it. So in this example, we're giving Expander the word hashcat, and you can see what it's doing to the word hashcat. It's chunking it up. The letters or the characters in the password will always fall contiguously, but it will start from the beginning and then chunk it up in sections continually. By default, Expander only allows 4 characters, so it's highly advisable to recompile that with either 8 or 10, depending on kind of what you're after. And 8 characters will give you the example shown in the bottom right. This is going to feed into another attack that we'll look at soon. The other tool we have here is Princeprocessor. Doesn't come as part of the hashcat utils, it's its own tool, and this is another candidate generator. But this takes a single word list input and then splits that into multiple elements. This is really, really useful when trying to attack passphrases instead of passwords. The example here is taken directly from the wiki. So if we were to say to Princeprocessor, give you this word list, rockq.txt, whatever you've got, and just give me 4 character passwords. These are the only options, the combinations we have to create 4 character passwords, and each one of these would be referred to as an element. So a 4-letter word would be a single element, of course, but we do have up to a 4-element passphrase down the bottom if we had 4 single character passwords. And it takes these all together from a single word list and combines them together in as many ways as it possibly can to create really, really weird and wonderful candidates. how can we feed some of these cool tools into some sort of more complex attack chains? So these are really, really nice when all your traditional techniques exhaust. So people are always familiar with running rules over dictionaries. You might be doing some low-key space brute forcing. You might have done some mask attacks. But when all of your attacks have failed and you've still got these hashes left to crack, where do you go next? These are the kind of areas that you might want to think about. The fingerprint attack is one. And you don't even need a word list to do this. If you've got a nice pot file from all of your previous cracks, what you can do is take the planes out of your pot file, which are clearly good passwords because you've cracked them in the past. So they're really, really good passwords already. You can run them through Expander. Always sort the output because you do get dupes, so make sure you unique them. And create a word list out of it. So you now have an expanded pot file of all of the previous things you've cracked. Then what you can do is run that in hashcat in combinator mode. And in combinator mode, -A1, hashcat will take 2 word lists, and if you combine that with itself, it just generates crazy, crazy passwords. Of course, though, this is dependent on how big and how varied your pot file is to begin with. When you've run that and attacked it, make sure you save the output of all those passwords that are cracked, because then it's a process of repeat and rinse, as you can see from the 3rd and 4th lines. Now, this works really well on really big hash lists, and what you'll find is you'll sort of crack more and more, and it will very quickly plateau, and then it will come down again. So depending on your diminishing returns, or more likely your patience, you're probably not going to want to run that forever. A standard basic Princeprocessor attack is next, where we're taking the most well-known and classic RockU, quite a small word list, RockU dictionary, feeding that into Prince, and we typically say to Prince, only generate candidates of 8 and above. Because when we're talking about fast candidates like MT5, NTLM, we've generally exhausted the key space of everything up to that point anyway. So we're not really interested in cracking sort of 5 or 6 character passwords. Pipe that into hashcat, and then options, business as usual, whatever you want to do, rules, so on and so forth. Jeremy Gosney, one of the guys on Team Hashcat, decided he was going to coin Princeception many years ago, and he figured, hey, why don't we take that output of Prince, which has already combined all of those elements, and feed it back into itself? And funnily enough, it worked quite well and created some really crazy candidates that, once again, traditional attack methods just will not get. In this example, and in the last actually, we've also got the -G, which is Hashcat's inbuilt self-random rule generator. So anyone who's cracked will know that they can assign rule files, but why not move to a more non-deterministic output and say, hey, Hashcat, I want you to generate 300,000 random rules, so you have absolutely no idea what's going to come out of this. The last example from Netmux, he found that if you put, like, for example, RockU into Prince and look at the top 10 passwords it generates, they'll be static every time you run it. But when he shuffled RockU, putting it in, it generated completely different candidates every single time. Crazy. Blew his mind. Blew mine too. So shuffling RockU and feeding that in, we're not only talking about more infinite runtime attacks now, we're completely in non-deterministic output. And you'd be amazed at how sometimes this will generate really, really crazy candidates that will help crack those last elusive hashes. We've been talking about passphrases a lot, so let's get into some delimited passphrase generation, because Prince and other tools are great at combining these things together. But what if you want to add delimiters, like a space, adding spaces between our words, writing a sentence, for example? Prince can help us with this, but it is a bit harder to do because we need to supply Prince with pre-delimited word lists. Prince only accepts one word list. So you will need to pre-generate your word lists with a space at the end to get Prince to help. And we've got an example syntax of that coming up soon. Another example, though, is combinatorx, which is in the Hashcat utils, if you download that. And it does have some advantages. It supports up to 8 lists. You can see in the example here, we've taken 3 basic word lists, file 1, file 2, file 3, each of which only contain 2 candidates. We can just assign those in Combinator with tac 1, tac 2, and tac 3, and you'll see exactly what it does. Generates, in this instance, 3-element passphrases easily. But combinatorx's true power is the ability to easily insert static or mixed delimiters with the separators shown here. So if you know the delimiter is either like a colon or a space, or you want to even mix and match them, you can use Combinator to create these candidates and then again feed those into Hashcat. So I'm not brave enough. We've had some amazing talks here that have done lots of live demos. I am nowhere near brave enough to do live demos. So we've got some little videos here just to show you what that might look like. And the obvious difference between the two is when you're running Combinator X, it's only ever going to take candidates from, in this instance, list 1, and put them as that first element. So it's going to go for the first candidate in list 1 and exhaust that first before it moves on to the next one. We can see this as all the cracked passwords start with the word the, whereas on the Princeprocessor side, it's picking out elements from absolutely anywhere it can, and generally you'll find it cracks things faster. The one thing we need to be really aware of on the Prince example is that because we need to feed Prince a space-delimited word list already, hinted at here, we've got the combined list 1, 2, and 3 from the Combinator X example, but we've appended a space to each one. The last candidate is going to have a trailing space. And a lot of users aren't going to do word, space, word, and then leave a space. Users don't tend to leave spaces. So when doing it this way, it's really important to add on -j and then close bracket, which is a single rule that truncates the last character, therefore deleting the final trailing space. Case toggling is also really important. As we've moved towards longer passwords and passphrases, people, of course, are starting to use capital letters more. And as passwords, like cybersecurity, is a human problem, not a technical one, people do tend to use capital letters either for the first element or for each individual element, as opposed to like camel case or doing other things. So here is a great example of how we can address that with some rules. Specifically, Yanis, who's one of the team hashcat members, has got a rule called the toxic 3 rule that's in hashcat by default in the rules folder. And some of the individual rules from that file are shown here, specifically the 3 and the E variants. I've given a screenshot of the hashcat wiki to show what these do, but they're really, really powerful for passphrases because they can toggle cases after specifically defined delimiters, or in the case of uppercase E, it can lower the whole line, and then every time it sees a space, it will auto-capitalize the subsequent character. We can see that in the rule 2 example, shown here, where we've got a vanilla candidate of can't crack this, or lowercase, but with an E, it will then can't crack this with capital C's and T. Really, really quick wins to try and emulate potential human behavior. The toxic 3 rule is also really, really nice when it's self-nested, because you can use more than one rule at the same time. So -r toxic 3, -r toxic 3, as well as with prints and other things. So here are kind of the examples in situ. I appreciate this is a password cracking talk, so it would be remiss of me not to actually give you some syntax that will work. The first two we've already kind of loosely covered in that video example, where we've got space-delimited passphrases in use with prints, and the Combinator X example. The third option, and there probably are more, but the third option, which is fairly well known, is shown at the bottom here. We're again using prints, but this time we're actually using the Combinator binary. A little bit more legwork is required to get this to work, because you have to create, in this case, list 1, which would be a single element, insert a space, and then combine that with another word list, and then add a space again, resulting in list 1. And then list 2, as the example shows, is just 2 words with a single inserted space. You have to pre-prepare those word lists. You can then run the Combinator binary from hashcat utils to combine those two together to get a 4-element passphrase with spaces throughout, but not at the end. Feed that into hashcat, and then business as usual. Run your favorite rules, run whatever you want to. In this slide, we've also got OneRuleToRule ThemStill. By show of hands, has anyone used OneRule to rule them all? A few of you, fantastic. Does anyone use OneRuleToRule ThemStill? Oh, OK. I didn't know how many enemies I'd made, because when I revamped OneRule to rule them all at the beginning of this year, the idea was to make the rule more efficient rather than to make it crack more passwords. So OneRule to rule them all, for any of you who've used it, is quite a large rule set. It had about 55,000 rules in it. There are other very, very good rule sets, and I often get asked, which rule set's the best? There's never going to be a best, because rule sets are used in different applications for different type of attacks and strategies. This was kind of created when I did this in 2017 to just be good against fast hashes. And I'm not claiming any original work from this, because OneRule to rule them all was derived from inbuilt hashcat default rule sets and some non-default rule sets. And I looked for the top performing rules over live data breaches to statistically give you the best chance of cracking fast hashes. MD4, MD5, NTLM, SHA-2 family, stuff like that. Absolutely do not ever think about using this over something like bcrypt or scrypt or anything that's painfully slow and computationally hard. when you're doing rule testing, always debug. Always debug. It's really interesting not to just prove the effectiveness of your own rules, but also to actually look and emulate human behaviors. So in this example, we're just running a rule, a standard rule dictionary attack on the left. But on the right, we're just doing a live watch on the resulting rule file, and we're sorting this so that the most popular rules are sort of like coming up to the top. You can, of course, just wait till your session is finished and have a look at this. But for the video, I wanted to show you live how that would kind of look. You'll generally find that the colon, which is the pass-through rule, which means don't actually augment the candidate at all, just test the vanilla candidate, will often be at the top. And then you'll see how many hits you get from different things. But it's really nice to see, and this is certainly a method that I used to derive the best performing rules when I originally created one rule to rule them all. OK, so on to rules, but more importantly now, buffer limits. When you're conducting dictionary attacks, so attack mode 0, the maximum password length when running optimized kernels, and most people who use hashcat will use -O, which is optimized kernels, is 31. There are some exceptions to this in some edge cases, but attack mode 0 with -O is 31 for fast hashes when using a dictionary attack. Some caveats to this, for example, are NTLM that will always have a maximum password length of 27 when running with optimized kernels. But 31 is kind of the overarching thing for fast hashes. Now, when we're doing this, we can actually see that there are rules we can remove and optimize out to make our rule sets more efficient. Some good examples are shown here. So on the left, we have just the word password in a word list. And on the right, we have what I've just called P rules. Because as we can see in the rule file, we've got P1, P2, and P3, which is duplicate the word once, twice, and 3 times. Password is an 8-letter candidate, as shown on the left in the first entry. So P1 is append password once, 16 characters. P2, append it twice, 24 characters. But P3, 32 characters, of course, is 1 over our limit of 31. So that does not execute. We've got a no operation. So it's only going to be the vanilla candidate that's passed in this instance. Similarly, with D, which is duplicate the word, we can see we have in.sec bang here. So D is going to duplicate that, as shown in the second row. We're then appending 1, 2, 3 to show how that would look. But then if we actually use D and then D again later in the rule set, D will not duplicate the original vanilla word. It will duplicate whatever is in the current buffer. So we've got D and then append 1, 2, 3. And we can see that down here, where we've appended in.sec exclamation mark again and added 1, 2, 3. But then we have another D. So that's going to duplicate both in.secs and the 1, 2, 3 again. And in this instance, adding an exclamation mark just for fun. Again, just to show how that wouldn't execute for the final example, a final exclamation mark pushes that over into 32. We're outside of our buffer limit, so that won't execute. But the candidate that is resultingly hashed, you can see, is the same as the one above. So if you've got rule files, in particularly ones that maybe you've created, but ones that you've sourced from wherever that might be, if we assume you're targeting passwords that are 8 characters and above, some of the ones shown here can very quickly be optimized out, because you are literally testing rules that will result in no operations, and you're effectively wasting compute cycles. Another interesting one is where the final length of the candidate is less than the intermediate length of the candidate. So you go out of bounds, but then you come back in. The actual final rule here is rule 3 shown at the bottom. But what I've done is I've appended to the rules step by step to show you how hashcat will process it. So if we take the password of super secure 1 bang, the first rule, we're prepending 1, 2, 3 to it. Fairly simple stuff. In rule 2, we're then P4ing, so we're taking that and appending it 4 times. Quite clearly, that is going to go way out of bounds for a maximum limit of 31, so that is not going to execute. Now, if we append in the final rule here, '9, which is truncate at the 9th character, that is within our bounds, because it's only going to be 9 characters long. So that P4 is now redundant, it's a no operation, and these can often be optimized out. Now, this could, of course, be really long and strenuous work if you've got big, big rule files. Luckily, there are a few tools that can help. Dupe Rule's been around for quite a while, and Vivaldi's got a slightly more modern tool called Rule Processor Y, and using these against rule files can often highlight some really big lists of redundant rules that you can really optimize out to make your attacks more efficient. OK, now buffer workarounds. So in a rule file, you have a maximum number of rule operations, and these are hard limits. So $1, $2, $3, append 1, 2, 3. That's 3 rule operations. You have a hard max of 31. and generally don't often see rule ops getting that hard. But you do have also a position buffer limit. We can only index 36 positions from the start of the password candidate. We know it's the start because it's always going to be position 0, and it's going to keep going. We can't index from the end. We can't index from the right left, but we can index from the start of our password going to the right. Again, the final rule is the important one here, but just to step through what's going on. If we look at the contents of our list here, we have quite a long passphrase there containing multiple elements. Just to show where position 36 is, in the second example here, we're inserting in position 36 the exclamation mark. 36 because we have 0 through 9, then A through Z. We can see where that appears right here, but we still have the word please afterwards. So we can't operate, we can't augment or do anything with that outside of our limit. So one way around this might be to reverse it with the R rule. You can see what that produces, a completely reversed password. But now we can operate on that because we've brought the word we want to use into an operable limit. So for fun, on the second one, we've reversed it, and then we've inserted the word let me in with an exclamation mark for the I in this instance. And we obviously have to insert that in reverse. So insert in position 6, the character N, in position 7, the exclamation mark, so on and so forth. And then when we finally re-reverse that at the end, we flipped it back, and you can see we've now got let me in. Moving even further, we can have sliding buffers. Now, I will absolutely say that this is going to be probably much less applicable to passwords because I would say how many of you are frequently cracking like huge password 7080, and then I'd be able to call anyone who put their hand up a liar, because I certainly don't. But there are other applications to this. Things like URLs get hashed, domains get hashed. For like game reverse engineering, internal file paths and file names can often get hashed too. So this is not just a password example, but I have put a ridiculously long 97 character password for the purpose of this slide. We can see our limit of 36 characters, and we want to change the word this. Just to show again, in position 36, this is as far as we can go. So why don't we slide the buffer left a number of times? And you can see that the front of the password's been taken off, and it's been bolted onto the end, literally sliding the whole thing left. We can then, in this example, insert in position 35 the number 1, not just insert, actually override the character in position 35 with the number 1, to change this to a this with a 1, and then slide the whole thing right, cha-cha slide, all the way back, and we can now see that the word this has a number 1. Again, of course, openness about this is going to be much less useful for passwords and more for other applications of cracking hashes. OK. Who's heard of Markov before? Markov chains or Markov modeling? OK, we've got a load of password cracking pros. I hadn't expected this. OK, Markov's fantastic. And Markov modeling is built into our tools like hashcat and John the Ripper and things by default. This allows us to really increase our chances of cracking passwords when brute forcing, because it will give us the best statistical chance of inserting a character based on the character that preceded it. So, if you've got a Q, the next letter could well be a U. And it will statistically use its own internal lookup table to say what character are people most likely going to use based on my model. If it's an S, what's likely to come next? Which means we can move away from naive brute forcing like A through Z, then AA, AB, AC. No one brute forces like that. So Markov is inbuilt by default, and hashcat's inbuilt Markov table is based on rockq.txt, okay? Which was derived from a real data breach in 2007, if I recall. So hashcat's doing this by default. But let's say you're in possession of a data breach. We've got a Minecraft-related data breach, which really happened. There was a data breach in 2016 called Lifeboat, which was a Minecraft community. So maybe the people who have generated Minecraft passwords are going to have more passwords that are related to Minecraft than of the structure of characters found in rockq. Reasonable to assume. We can tell hashcat to ignore its internal lookup tables and use a Markov table we supply. So what I did here was I went online and Googled lists of Minecraft items, Minecraft objects, worlds. I don't play Minecraft. My kids do. Maybe I should have listened more. And I got a huge list of Minecraft-related words. I ran them through OneRuleToRule ThemStill, and I created a word list of, as you can imagine, heavily augmented and permeated Minecraft words. Then I took hc-stat2gen, which comes as the hashcat utils package, and this is for creating Markov tables. So I created a table there in step 2. You have to compress it to make it ready and sort of supported by hashcat. But in the last example, highlighted in red, if we add Markov hcstat2 and supply our own Markov table, hashcat will then use ours instead of its own inbuilt knowledge of RockQ. And just as a test, I let this run for 1 hour, 60 minutes runtime using hashcat's default and then the Minecraft Markov model that I just scraped from a couple of Minecraft wikis. And in 1 hour, it cracked nearly 12,000 more passwords in the exact same time. 12,000 passwords I would have otherwise missed on cracking if I just let hashcat do its thing. Unicode. OK, Unicode's fantastic. So when we talk about Unicode, we are now talking about outside the normal 95 printable ASCII characters and extended ASCII. There are huge numbers of Unicode objects, and this covers things like not just emojis, but foreign languages like, for example, Arabic or Greek, that I hope are viewable in this slide, not to mention other Asian-based languages and many, many more. Tip of the hat here to Yanis again from Team Hashcat. From that one-liner at the top is a nice, quick and easy way of printing Unicode characters on the command line based on Unicode page points, code points, which you could look up, as I've done here on the right. We have an example here. So the Arabic alphabet uses Unicode code points 0600 through 06FF, which we've then applied up here. And it's actually shown here in the second example, so we can print out all these Arabic letters, for example. You can also note that we do get the UTF-8 hex representations of these on the website that I've used in this example, but you can find these anywhere. And it's interesting to note that Arabic letters use 2 hex bytes to represent a single character. Okay, so Unicode can use up to 4 bytes. Emojis use 4, which makes them very painful in a number of ways. But you need to know this because it's very important when we are attacking in hex. So working in reverse order on this slide, in the bottom example with emojis there, what we're doing is we're taking all of those possible permutations of code points that represent emojis. Luckily for us, the first hex byte of any emoji is always going to be F0. So we've created custom character sets for it. Similarly, the second byte will always be 9F. The third byte could be 98, 99, 9A, or 9B. And the fourth byte could be any of that. We're never going to blindly test them all, because that would be a massively extra key space that we know we're not going to hit characters for. We can then tell hashcat to process this in hex with the hex char set switch. And ultimately, when we apply our mask, you'll see we've got question mark 1, 2, 3, and 4. We need to do that because those 4 characters is only going to represent a single emoji in this instance. You can also pass literal characters. So in the Arabic example at the top, if you've got the literal UTF code point for the Arabic characters, or Greek, or whatever you've got, it doesn't matter, you can pass them to standard in through hashcat, and you can crack Arabic passwords, for example, as shown on the right. So we can do this in a number of ways, both with literals and with hex. So emoji rules, yes, emojis do in fact rule. People do actually use emojis, and if we're using emojis in our rule sets ourselves, we do need to append them or prepend them respectively, and we do need to escape the X with a backslash. And you can just see here in a really simple example how you could take any Unicode characters, not just emojis, and use them to either append, prepend, both, do whatever you want with them. Hashcat does support these, and you can attack these if you've looked up the respective hex characters. People really do use emojis in their passwords, OK? I've not made up this data. You'd be amazed at the weird and wonderful things that you find. I admit, yes, for those pen testers out there, every time I'm in a domain and I've ransacked AD, I'm not going to be really cracking many NT hashes with emojis in them, granted. But you'd be amazed how many people select them when creating accounts on mobile phones these days, especially. So this does happen. It is real. The next cool tool is Tomesis, which has been around for a good while again. I keep referring back to hashcat utils. Tomesis will take 2 word lists and then produce insertion rules that you can then use to augment a password list that you give it. In this example, we've just got 1 through 5 and password. It generates rules, which you can then use in a dictionary attack. And it can create weird and wonderful rules. Obviously, with more words, it gets absolutely crazy. And you can see your words getting inserted per position. Tomesis does have a slight limitation that it only indexes up to the first 15 characters. But there are also other ways to do this. Yanis actually, I haven't got permission. I was speaking to him about this. I don't have the code to give to you for this, because this isn't a rule generator, but an actual clear text candidate generator. The only reason I can't share the code with you is I have it on good authority. This is going to be appearing in either default hashcat functionality or in hashcat utils quite soon. So watch this space. Even so, you can see how kind of weird these passwords start to look. So when you get these candidates, don't just stop there. Start to play with them, start to augment them, start to use prints and expander and feed these into other attack chains, as we've seen before. OK, transliteration. That is a clear text password there in ASCII characters. OK, who reckons they can crack that? By sheer virtue of the fact that I've asked that, no one is going to put their hands up because it sounds like a trick question, and it is a bit of a trick question. That looks like a pretty good password. And do you know what? For all intents and purposes, based on the length, the key space, and stuff like that, it kind of is. However, it's really interesting to note that if we take the NT hash of that clear string and search the have I been pwned passwords list for it, it appears in over 200, nearly 250 data breaches. Now, that's a really random number, a really high number of times to see that fixed string. And that's because, actually, that fixed string isn't so random. Okay? Particularly in Taiwan, where the Zhuyin keyboard layout is used to represent certain Chinese characters, that ASCII string that you see at the top is actually the word my password when entered into a Zhuyin keyboard layout. Okay? So this is like crazy. When I discovered this, it was like blew my mind, and it still kind of does. It's kind of weird. We can see how the two letters, like JI and then the tone, 3 in this case, are kind of used to translate the literal characters here. And this is really weird. The first thing I did when I saw this is I loaded up a Zhuyin interactive online keyboard layout, and I pressed JI, and then it gave me like 27 symbols to choose from. I was like, holy shit, what am I going to do here? So this is not an easy thing to figure out. There are lookup tables, and I don't know how many of you are frequently cracking Zhuyin-based keyboard layouts or others, but this is pretty cool because it's the transliterated password that's hashed, not the respective Chinese characters. So this is why we can see a password like that, which seemingly looks incredibly random, more often than you might think. Now, that in itself raises the question of entropy. Now, entropy, I'm not debunking it. Entropy is very, very good. It's tested. It's a very good statistic. But it's only a very good statistic in the edge cases where we're having like systems and computers generating passwords, not humans generating passwords. Again, we're kind of like the problem here. If we look at the entropy of that password there, we can take the log. Pretty easy to work out. The log of the key space, 36 characters possibilities, 26 lower alpha, 10 digits, raised to the power of length 12. Okay? That gives us about 62 bits of entropy. There could be far worse passwords out there than that, quite clearly. But societally speaking, we're only really quantifying the look of the password, not the actual degree of randomness. And that JI example we just saw is a perfect example of that, because you'd look at that and you'd think, that's got tons of entropy. It's 12 characters long, that's got... But actually, it kind of shifts our perspective of real entropy and what that represents. So I'm not here to debunk it. I'm just here to say that you need an actual computer-generated password that truly is random to really apply this. It's crazy, like I said, and 0 people do this, because every time you run hashcat, you've got Markov. It's doing it for you by default. So you are never really ever conducting a completely naive, unintelligent brute force attack. You are always generally getting a lot of help. You just don't realize it. OK, the last kind of section, hash upgrades. So one of the hashcat core developers, Sam Crowley, who I've got a shout out to in a second, put me onto this. This is really, really nice. And this is the leading on to the cracking hashes with hashes. If you've got applications and you're upgrading the security for your users, what options do you have? Do you get them to reset their password and then make the hash stronger? Do you update them on the next login? Do you rehash the hash? OK, so some things that you do actually see is, let's say you've got a database that stores the MD5 of your users' passwords. You want to beef up security. I get it. Hey, this is a positive move. So what you might do is bcrypt your MD5. Okay? Now, this does actually present a problem. I've given an example of what that might look like here. With MD5, the string insecurity, and then we've bcrypted the resulting value. Hashcat supports this, mode 25600, and we can see that. Now, the interesting thing is, in this kind of example, we can actually attack the inner hash, not the resulting bcrypt hash. And this is really, really interesting. And the upshot of this, I'm treading on my own toes, is never, ever get rid of your uncracked hashes, specifically NT if you're a pen tester, but also SHA-2 family ones. We've got a user. User's created a password here. It's a pretty good, not uncrackable at all, but a pretty good password. That user has reused their password on 2 websites. We're not uncommon. Unfortunately, we are simple creatures, and we like to reuse our passwords. Those two sites then get breached, and an attacker gets possession of them. The attacker might do a fast hashcat run. It might look at some write-ups. It might, however it identifies, once the attacker realizes that breach site 2 is doing this and decrypting the original SHA-256 hash in this instance, what they can do is they can take a list of their uncracked SHA-256s, run them through bcrypt, and if they're lucky, they get a resulting hit. If they get a hit, they now no longer have to crack a bcrypt hash, which is slower than, it's like this arguably one of the slowest hashes you can crack. They now only have to crack a SHA-256 hash, okay? And these specs are based off an RTX 3090, not the latest and greatest. But anyone here who's done pen testing, you don't get out of bed for bcrypt. Unless the password is like password123, I'm not getting out of bed for bcrypt. Slight exaggeration, but needless to say, 87,000 guesses per second is substantially lower than 9.3 million guesses per second. So if the inner hash is fast and, very importantly, unsalted, because the attacker wouldn't really know the salt of the inner hash if they're able to identify it, this could be a thing. And this is why I say never, ever delete remove your uncracked hashes. In the Windows world, because I'm a pen tester, so I do this a lot, this really applies to like NT for me personally. And this really comes into its own for those of you who use Responder, who do SMB relays and stuff like that, when you're capturing those NTLM v2 hashes. When you actually peel back the layers, most things in Windows world have NT hashes in them. They all do. Domain cache credentials are just a double computed NTLM hash. NT is used in Kerberos. It's used all over the place. So if you've used Responder and you've got an NTLM v2 hash, or you've got domain cache credentials, I have it on good authority that at some point in time we'll also get some Kerberos variants for this too. You don't need to crack the NTLM v2 hash with the password. You can crack it with an NT hash that was used to generate it, which is absolutely awesome. In the bottom example you can see here, we've got a single hash as a word list, and we've cracked that NTLM v2. Now, you still don't know the password, but in Windows, you've now got the NT hash. Pass the hash. Business as usual. A password hash is as good as a password in Windows world. So don't ever, ever, from now on at least, I'm hoping now loads of you are going to go back and you're going to remember this. You're going to have an uncracked NTLM file or an uncracked SHA-256 file. I'm not saying your chances are high, but over time, as you don't crack more and more passwords, you're going to have a bigger and bigger repository of uncracked hashes that you could then use to do this. This is called hash shucking, shucking off the outer hash and attacking the inner hash. OK, password storage. Coming towards the end now. Appreciate this isn't password cracking related. But I've been standing up here like ranting for ages about how we attack passwords. It would be remiss of me not to kind of say, how do we do things kind of well and good? If you look at OWASP, we've got some recommendations here. Argon2ID, scrypt, and bcrypt. Now, bcrypt is unintentionally cache hard. It wasn't made that way, but it kind of is. And when we say cache hard, we mean we can keep bcrypt generally on the CPU in level 1, 2, and 3 caches without it spilling over into VRAM, which is what your graphics card uses and what dictionary attacks and hashcat uses and leverages for GPU acceleration. scrypt and Argon2 are really, really memory-hard algorithms. Now, there's been lots of back and forth about which is better, but cache-hard is generally the way to go. For authentication, at least, unless you've got long runtimes, bcrypt is better than scrypt and Argon2 for runtimes of less than 1 second. If you go beyond that, then there are, of course, points where things change over. But by and large, although scrypt and Argon2 are great KDFs for general key derivation function work, for real-time authentication, okay, we're kind of good with this. Bcrypt has been tried and tested for a long, long time. Jeremy Gosney, who goes by Epic's OIP there, has also kind of brought out about a year ago HMAC bcrypt, which is really, really powerful, although we don't, unfortunately, have support of it in our tools yet. But as far as password security is concerned, it's fantastic. It uses pre-hashing and post-hashing. So it uses HMAC SHA-512, adds a pepper. The pepper is going to prevent shucking straight off the bat. Base 64s it. It then bcrypts the value and then post-hashes it again with HMAC 256. Get your pepper, store it in an HSM, keep that safe somewhere. That overcomes broken implementations of bcrypt that do exist, and that overcomes bcrypt's 72-byte character limit as well. So it's really, really good. We're just not far enough along yet to get the uptake that I feel it deserves. OK, for anyone who loves password cracking, it's like cocaine for me. I just love it. Ever since I cracked my first hash, I thrive off this. So we've got some free password cracking. It's free, so I don't mind kind of putting it here. 15 YouTube videos, 4 hours, VM to download, pre-packed with questions and answers. It doesn't cover all the things that we've covered today, but it covers some of them. Like it does cover prints and some emojis. Have some fun with it. We've had really good feedback from it. We've got a Discord channel on our server if you've got questions about the training. And this is the one, if you're a password cracker, this is the one to take a photo of. So if anyone can, tweet me the clear text value of that hash, and I've only given you one small hint on the second line, we'll give you a challenge coin. Unfortunately, we only have hacking ones because we've just taught our hacking training at SecT, so it won't be a defending course, but you'll get a coveted glow-in-the-dark challenge coin if you can tweet me the clear text of that hash, and that's all I'm going to say on it. But with that, I don't think I'm too much over time. Thank you very much for listening. I hope you enjoyed it. And we do actually have on our website from a few years ago a CTF, completely free. Don't let the URL fool you. There's no cryptocurrency prize anymore. It took someone 4 hours to swipe that. But the challenge is still there. And the following blog post has all the answers for you as well. So thank you very much indeed. And thank you, SecT, for having me.